Our next guest is Jon Morehouse, correct? Okay. And his fun fact is that he can tell you the exact date, time, and location of where he wrote his very first line of code. And it's not where you think. Jon Morehouse, everybody.
So I will announce where I wrote my first code after the talk. But yeah, so thanks for coming. I'm Jon. I'm going to talk a little bit about BuzzFeed, our engineering, an API gateway, what it is, and why building it in Go was totally perfect. So let's do a little intro. First, 5 reasons why Go is amazing for this service. It's great for prototyping. Concurrency is great. It's really fast. Standard libraries, amazing. It has great hooks to build what you need. Again, fast. And all this kind of comes together to build future-proof systems. How about some background? So I'm basically the person at BuzzFeed who everyone has to say, don't rewrite this in Go. I'm an infrastructure engineer. I love Go. I like Rust. Python's fun sometimes. Distributed systems are sort of the things that I really, really get excited about. And that's me. Let's talk about our history. BuzzFeed, we started as a big web app. It was a large amount of Perl, a large amount of fires, and a lot of stress. We started building services. We kind of just built them as we saw fit. We didn't have a lot of consistency, and that was fun. We started to get sane about how we build services, and we built a true SOA environment. And that's put us in a better spot. I think a better, more fun way to put this is we had one really big fire that everyone rushed to. We had some smaller fires, and we had no fires, which is a good spot to be in. So let's talk about our culture. We prefer simplicity. So this means you don't probably need 5 databases for your 200-line service. We stick to Python first. Observability is really important to us. I'm pretty sure most of my comments on PRs are about metrics, logs, instrumentation, things to alert about. And that's probably a good thing. And finally, we really like to experiment. It's fun, it's fast, it's quick. Today, we have a consistent way to deploy services. We're on containers. We built sort of an internal tool to help us manage that and productionize those. This is the part that's most interesting to me. This is our API gateway. We built a single sane way to communicate. And we ship a lot of GIFs. GIFs and BuzzFeed are one and the same. This is what it's like every day at the office, building and writing code. So all that came together, and it helps us support 100 engineers, 50 APIs, and the 200 services that are talking to those APIs. Things have gotten a lot easier. Part of my team, as the infrastructure group, sort of our goal is to focus on the engineering experience. What do I mean by that? I mean that basically we want to focus on making it fast, easy, quick, and robust to build, deploy, productionize services. It's got to be fun working at BuzzFeed. The typical BuzzFeed service has a few characteristics. It's an API, JSON, HTTP, talks to a lot of other things. We usually use Python. We use Tornado, which is an asynchronous networking framework. It works for most cases. In the past, almost everyone brought their own authentication, ACL, and rate limiting, and it wasn't a great thing. It wasn't fun. Here's an accurate description of trying to talk to different services. It's like trying to pull across basically a freeway in LA with a school bus. Not fun or easy, and it was just, in general, taking a lot of our time. So again, as the infrastructure group, my team, we're responsible for finding these problems and sort of fixing them. We prioritize like how we can make things easier, how we can make basically the lives of our engineers better. So the first thing we did, we broke it down into some problems. We said, there's no single way to talk to different services. There's absolutely no way to observe them. We had no idea what was going on. It made us vulnerable. If someone was attacking one of our systems, we had no idea who it was, where they were from, or if it was even one of our services. And finally, to talk to a lot of services, there's a ton of boilerplate. If you're building a service, you're bringing your own authentication, your own ACL, your own rate limiting. It was just too much boilerplate. So as companies grow, the small services problems become bigger problems. Your problems will scale. This became the same with us. We had no idea who was using what. We had a bunch of stuff laying around that was being managed, maintained, wasting money, that we could get rid of. The problem was we had no way to understand who, what, where those services were. So let's talk about the solutions. This is where I get really excited because I immediately want to go build something, and everyone's like, just let's focus, calm down. So we came up with some solutions. We said, hey, we need auth, we need ACL. We can provide that for folks. We can provide that for all our services in a single way. We said, we need rate limiting. What if we provided that to prevent bad actors, just out of the box? What if there was a single way to talk to anyone within the infrastructure or the ecosystem of BuzzFeed? What if you could just do one thing to talk to any service you wanted? And finally, and most importantly of all, we decided that, hey, we need a single way to promote observability. This is an accurate picture of me running to work late the next day because I immediately went home and started building a bunch of stuff, trying to solve these problems in Go. So we had these problems, and we said, hey, we know what the solutions are. Let's take a look. Let's take a look in the open source community, and let's look around and see what it would take to build it ourselves. Obviously, a lot of folks in here know that this is sort of Go's community sort of sweet spot. There are some really, really great tools that deal with microservice communications. There's so many great packages and projects out there. We looked at all those. We looked at what it would take to build it ourselves, and we started coming up with a set of goals. So these are the goals we came up with. A lot of these goals are sort of principles of any good Go application. Go applications are quick, simple, observable, future-proof, and predictable. One of the things that we really wanted to make sure was that we said, hey, any system that we work with, that we use, that we put in production, we can predict how it's going to respond to load and how it's going to work in production. We started going through it. We looked at some of the systems that we found, and one of the problems we kept coming back to were the open source alternatives that we had found actually had very complex dependencies. For instance, we at BuzzFeed primarily rely on Redis and MySQL to solve almost all of our problems. We have great operational understanding of it, we have experience, and we just felt comfortable using it. We didn't find that in the community. For what it's worth, we also took a look and we said, hey, how can we build this? It turns out that we didn't need to first build it in a super fast, crazy way. So we were able to use our tried and true tools, Python, Tornado. We could build out a very small tool set, and we could basically ship something that solved those problems quickly. This is the classic build versus buy problem. So sort of looking at those dependencies and the problems that we had seen in other systems, we decided to build it in-house. One of the things that we really wanted to focus on was observability. That's the key point up here. We were comfortable building a system that was quick, and we knew that we could get something that into production in just a week's time or so. And we knew that if we relied on MySQL, Redis, and just the basic tools, that we would have a good understanding in terms of operations. We would know how it's going to respond, how it's going to scale, and sort of some of the things that we want as operators of a system. The key here is observability, because we wanted to observe not only our own system, but everyone else's systems too. Every system that was behind this service that we were providing, we wanted to be able to say, hey, as a service user or a consumer or an owner, we want to make sure that you have every insight you need just in one single place to observe how everything is working. Enter the gateway. So the first version, we actually built out, most of it was built on an airplane, believe it or not, with no Wi-Fi, which was really cool. We productionized that Wi-Fi or that airplane code base in about a week. We provided immediate value. One of the keys when you're shipping a service, especially at the infrastructure level, is that whatever first version you ship, you provide value and you get feedback. Importantly here, and this is going to go back to the Go part, we came up with a really good contract. We know that Go services are great. Microservices in Go is sort of its sweet spot, especially with networking. So in the back of our heads, we sort of said, hey, if we ever do write this in Go, we want to have as minimal surface area as possible so we can focus on exactly the problem here we need to solve. We came up with a very strict contract. So as we productionized this, going back to the contract, we learned a lot of things. We realized that simple token auth was great. It worked. It provided the developer experience and everything we needed out of the box. For a first pass, rolling rate limits were perfect. Just by saying, hey, how many requests has a service made in the last 10 minutes was great for 90% of our cases. Finally, we realized that basically making it easy to onboard upstreams was the most important part. We decided to build a central proxy because we had a lot of services, some in Perl, some in Python, a few in Go, and we realized that the easier it is for these services to get either behind this service, this proxy, or use it, the better. So we wanted to make sure that they had minimal places to update to make their service available. Finally, we learned that concurrency is really important. Going into this, we had thought that the rate limiting algorithm, the authentication algorithm, those would be really hard to scale, really complex. We realized or thought that Tornado, and it's an asynchronous framework, it's an IO loop driven framework, this would be its sweet spot. Just making a bunch of proxy requests would really work. That's what we thought. Speaking of the contract, we came up with a really great dashboard. This is the value that we provided day one. We basically said, hey, if you're a user, go to this dashboard and take a look at exactly how your service or any other service is responding to load, handling load, and in general, if it's just available. This was sort of the contract that we gave to our users. And we also built a dashboard for ourselves to help us maintain it. As operators, sometimes you want a lower level granularity of metrics. And this gave us the observability we wanted into some of those things. So concurrency. Some of the things that we came up with and that we noticed as we productionized the system, that it wasn't predictable. One of the characteristics of a very highly scalable system that you can grow with as a team is that you can predict its operations. You know how many resources it needs, you know how it's going to respond to traffic spikes and things of that nature. We realized that that wasn't the case. Because we didn't have the ability to control traffic to each upstream, we didn't have a way to sort of limit that concurrency. We really started to struggle with things such as like noisy neighbors. If one service was getting a lot of load, it could affect another service in the same as another upstream. For what it's worth, we have some slow services, we have some fast services, and we didn't have the ability to apply back pressure. There was no way to say, hey, service A can only handle 100 requests a second, don't give it more than 100. We didn't have that control yet. Finally, these were some of the things that we had fought with a little bit in the past and hadn't been an issue at scale. But we didn't have great support for asynchronous drivers for Redis, for MySQL and Tornado. It turns out that in Python, all DNS lookups are synchronous, and getting asynchronous DNS was hard. As a team, BuzzFeed has a lot of Python engineers. We have a lot of experience with networking and Tornado specifically. And we started to feel that we were fighting fights at the wrong abstraction levels. That's not a good feeling for a service that's only a few months into production. We felt that we had sort of used up our headroom of sorts in terms of optimizations. We didn't feel like we had a lot of room to grow with this system. So it turns out that my team of 4, we all had experience with Go. I mean, myself personally, like I'm really passionate about Go, and I think that my teammates get annoyed with me because I rub it off on them a lot. But we also knew that this was Go's sweet spot. We knew that we had a small service, and we're like, we have a small service. We know that Go's good at this. What if we started thinking about what it would look like to experiment and see if we could, potentially replace this system? So we prototyped. We had an engineer. We just wasted one engineer's time, worst case, and we took a week. It turns out that one engineer was me, and these are the emojis that I sent probably thousands of times throughout the week on Slack as I was building this service out, because it was great. It was fun. So let's dig into the Go version of this API gateway. Let's talk about sort of some of the characteristics of Go, how we leveraged it, and how we built with this system to take it from a prototype to a production system that is something we can grow with in the long run. This is the first version. If you sort of follow the code paths, we rely a lot on two things. The standard library. If you notice those last lines, 17 and 18, we use Go's reverse proxy. This just did everything we needed out of the box. And those two lines replaced about 200 lines of buggy Python code that we had to deal with. It's also interesting, when we were debugging the Python code, I referenced the single host reverse proxy source code to help debug some of the problems in Python. So here, we're just doing everything synchronously. Behind the scenes, Go's HTTP process basically kicks off each request in its own Go routine. We realized that we would get concurrency out of the box, and we sort of leaned on the runtime. We know Go is fast. It's good at doing a lot of things at once. And we realized that by just sort of letting it do its thing, we could focus on things that were more important to us in this first early version. So speaking of standard lib, one of the things that's really beautiful about the standard library in Go is that it gives you these great abstractions. I think we have 3 or 4 dependencies total in this system, and they're mainly just for Redis and MySQL. So it's really a testament to what you can do with Go standard library. Here's a case where, again, we're using that reverse proxy, and we wanted to add timeouts, and we wanted to instrument exactly how long connections were taking. It turns out that Go has some really great hooks, which is a really magical experience as a developer. I didn't know about transports before this, but it turns out that when we wanted to add instrumentation, it was as simple as writing a wrapper around the built-in transports, adding your own dialer, and doing whatever you wanted to control the TCP connection cycle in said dialer. This is a great example of Go has a great abstraction layer that also lets you dig in deep. In Python and Tornado, this wasn't exactly the case. We felt we were fighting things and doing magic behind the scenes. To me, this isn't magical. This is very straightforward, very easy, and it's a testament to Go's standard library. Here's an example using a very similar piece of code where we added DNS lookups. Adding our custom DNS lookups were a matter of just adding a few lines of code and writing the instrumentation that we wanted. Why did we want to instrument DNS? Well, we had found out earlier that DNS was somewhat slow and it wasn't predictable. It turns out that inside of NetDial or NetDial in general, if a record is not resolved, if it's a host name or something like that, Go will automatically resolve it. For what it's worth, out of the box, Go has concurrent DNS lookups, and that was great for us. But we actually wanted to time exactly how long each DNS record took to look up so we could understand our own systems. That was, again, really easy. So I talked before about concurrency and how we didn't have a great understanding of how we were handling requests. We didn't have the ability to apply back pressure. We didn't have a way to say, hey, I'm operating a really slow upstream. Don't send me more than, say, 100 requests a minute. It turns out in Go, as we took another pass at concurrency, it was really simple. By adding a buffered channel and having a set of workers, we could try to submit a job. And when that job failed to submit, we knew that we were at capacity. We could immediately apply back pressure to whatever service is working with us. We didn't even try to send the request along, so we know that we weren't sort of adding fuel to the fire. And it was really simple. Here we're just using basic Go build-ins, and it was just a testament to concurrency being first class in the language and actually coming out in a production system to be very useful. For what it's worth, this also is very simple. It's just a few lines of code to add a very complex, what would be very complex in many other languages for us. Here's the other side of that worker pool system. One of the things that we really wanted to think about was how do we model concurrency? We have a set of dependencies. Each worker has maybe a set of connections that it's using, it's pooling. And we wanted to say, if each connection or if each worker is working in isolation, how do we remove the need to synchronize between those? How do we basically model our asynchronous concurrent code as basically top to bottom synchronous? How do we make it simple? It turns out because Go routines are cheap, easy, and in general just lightweight, we could add dependencies and we could scope them to the workers themselves. What does this mean? We don't have any synchronization points across Go routines, and it turned out to be really simple. So productionizing this system worked. It was something where I was hoping to get a trophy like this at work. What's kind of funny is that no one noticed. Like literally no one did, but I think that's the beauty of it. We were able to take a system, replace it in production without anyone knowing, and save some money along the way, build a good code base, and learned a lot about Go. So finally, why Go? Going back to the first slide. It was easy to prototype in. We could lean on the runtime. Concurrency was great. It was really powerful, and it let us have the control we needed. Standard library gave us the ability to basically use abstractions from day one, but also build with those abstractions. As we needed to expose metrics, the right hooks were at the right places for us. Finally, it's just fast. It's very performant, especially under concurrent workloads. And all this sort of came together to make a very future-proof system that we can build with, work with, and grow with as a team. And that's it. Thank you for your time.
Awesome. Thank you very much, John. That was great.